Hello, in this video I'm going to show you how you can use potentiometers with your Arduino to send MIDI. And I'm going to show you how you can code this from scratch so you can use MIDI messages such as MIDI control change. So let's get started. Hello and welcome to The Nerd Musician. My name is Gustavo Silveira and this is the series MIDI Programming for the Arduino. Here I'm showing you how you can code from scratch your MIDI controller with different things. We already saw how to use the Arduino IDE, about variables, arrays, for loops, how to digital read, digital write. We learned how to use the MIDI USB library so you can make our Arduino a MIDI class compliant device. And we learned how to code buttons. So if you didn't watch those classes, please go there and watch them first, because we're gonna use the concepts we learned in the previous classes. Also, it's important that you watch the DIY MIDI controller workshop, which I have the link here below. There I teach you all the basics about Arduinos, breadboards, how to wire buttons and how to wire potentiometers. And there I teach you how to use those without actually having to code from scratch. But that's exactly what I'm going to do here today, teaching you how you can code potentiometers from scratch. Today we're going to need an Arduino Leonardo, which can be turned into a true USB MIDI class compliant device. So you just plug in the USB and it will be recognized as a MIDI controller. Linear 10K ohms potentiometer, also known as B10K, a breadboard, and jumpers. Before we do our circuit in real life here in my table, let's go to Tinkercad, where we can do this in the browser and we can actually run a simulation. The link for the Tinkercad class is here below. Also, I already taught you how to use Tinkercad in the previous classes. So let's add an Arduino, a breadboard, and a potentiometer. So first, what is a potentiometer? A potentiometer is a variable resistor. A resistor is something that decreases the amount of current passing through it. So if you want to decrease the amount of current, you can use a regular resistor or a potentiometer. So a resistor will have a fixed value, while a potentiometer will have a value that changes while you turn the shaft here. So it will have a minimum and a maximum resistance. And this one, the B10K, is a potentiometer with 10K ohms of resistance. Also, it's linear. And being linear means that when you move the knob, it has a linear response, while the log or the A potentiometer will have a curve. That's usually useful for audio applications, but for MIDI, always use linear. So how do you wire the potentiometer? The potentiometer has three legs or three terminals. The first one, which is the terminal 1, we connect to ground. The third one we connect to 5 volts. And the middle pin, which is the wiper, we connect to any analog input of the Arduino. And the analog inputs start with an A. So I'm going to connect my potentiometer in pin A0. So how do we read the analog pin? And in the analog pin, we can read any analog sensor. So this class here today can be used not only for potentiometers, but for any analog sensor, okay? So let's start with pot state. So pot state is a variable that will store the state of the potentiometer. We don't need to declare analog pins because they're always input. They can't be output analog pins. Let's start our serial monitor. Now let's read the state of this pin and store in our pot state. And the way we read an analog pin is through analog read and the pin, which would be a 0. We're also going to use a variable to store the pin number. So let's put here pot pin and then serial.println pot state. Let's select our board. I'm using Arduino Leonardo. I'm going to connect my board here. Now let's copy this and paste in Tinkercad. Let's come to text and run the simulation. You can see here that we have a reading from 0 to 1023. That's because the Arduino analog pin has a 10-bit resolution, and 10 bits, which are combinations of 10s, 1s and 0s, can give you 1024 numbers from 0 to 1023. Also, another thing we can do here is add an LED. I'm going to use the LED on the pin 13, the built-in LED. So I'm going to declare the LED pin on pin 13. I'm going to declare as an output, and now we can emulate an analog output with the LED. I'm not going to get into details about PWM, how they work, but PWM is a technique that we can emulate an analog pin in a digital pin of the Arduino. Again, I explained that in the DIY MIDI controller workshop, but just be aware that we can use a digital pin as an output, but using this PWM technique, we can emulate an analog pin. And what can we do with that? We can decrease or increase the brightness of an LED, we can move a motor, and so on. So what I want to do is doing analog write, then the pin of the LED, and then the value that I want to write in this analog pin. And this goes from 0 to 255. Doesn't go from 0 to 1023. When you want to analog write something, your resolution is of 8 bits. So you have 256 possibilities. So from 0 to 255. So I'm going to create a variable called LED value, and I'm using the byte variable here because the byte variable has a size of 256 and I don't need anything more than that. So I'm gonna use this LED value. So I have a reading that's from 0 to 1023, but I want to use a range of 0 to 255. How can I do that? So we can use the map function. The map function transforms one range into another range. So I want to store in LED pin this mapped range, and the way we do that is map, then parentheses. The first argument is the value we want to change, so it's pot state, then the original range of pot state, which is 1023, and then the new range, which is 0 to 55. So sorry, it's not LED pin, it's LED value. So now we should be able to change the LED brightness. I pasted here the new code. So you see that we are moving here, but our LED is only turning on when we get to 500 and something. That's because I made a mistake here and used the pin 13 instead of a pin with PWM. I was thinking about the Leonardo, which the pin 13 is PWM, but here it is not. So here, instead of using the pin 13, we'll have to actually use a resistor. So let's use a 220 ohms resistor, and the LED. Doesn't really matter in which leg the resistor is. So as long as the cathode is in the ground and the cathode, which is the longer leg in the LED, is in a digital pin with this tilde here. See, so those pins with the tilde are PWM pins. So now in our code, let's change pin 13 to pin 5 and start simulation. Another mistake, I have the wrong column here. Let's try again. You can see now that we are changing the brightness of the LED. Okay, so now you know the basics of how to read an analog pin. We used the analog read function to read the analog pin, and we used the map function to change the range of the analog read. Okay, so the first thing I want to do is adding more potentiometers. So you can start using arrays for loops in the same way we did with the buttons. So we have a modular code where we can just change the number of potentiometers and the pins, and the whole code changes because we're doing in the same style we did with the buttons, using arrays and for loops. I'm just adding one more potentiometer. It could be 2, it could be 3, 4, 5, as many as analog pins you have in your Arduino, our code won't change. So let's take a look on what we did with the buttons. We have the number of the buttons, then we have an array for the pins, for the note, the button state, P state, the bounce, etc. So let's use some things so we don't need to rewrite everything. So we're going to use the MIDI USB library. and I know we're gonna use this kind of thing. So I like to just copy and pasting to make it faster. So for example, I can copy this, Command C, Command F to search, and then I can replace this button pin with pot pin. And we can click here, so it will replace all. But I know it's going to be pot CC, which will be the control change we're gonna use. Button state is going to be pot state, and button P state, pot P state. So first thing, we want to create a for loop. Oh, I missed here, and pots. So here I want to store in pot state at I the analog read of the pot pin at I. That's similar to what we did with the buttons. So we created a for loop, and we want to store in the button state the digital read, but here we want to store in the pot state the analog read. So now let's print pot state. I'm going to add a space because we're going to print the state of a potentiometer, add some space, then the next potentiometer, add some space, the next potentiometer, and after we read all the potentiometers, I'm going to add a new line. I need to close the for loop here. Sorry, it's not a parenthesis here. It's this curly braces. Okay, I need to delete this parenthesis. It's giving me that here. I have n buttons, and it's not n buttons, it's n pots, so we can just do that. Done compiling. We have actually two potentiometers, and they are in A0 and A1. Pot CC is not necessary yet, but let's choose CC, let's say 11 and 12. Let's paste here and see what we have. We can add the MIDI USB library to Tinkercad because it doesn't accept libraries. So let's comment that. Okay, let's see in the serial monitor. We have the first reading. It's not reading correctly because I did something wrong here. Okay, we have our two potentiometers working. Next thing I want to do is changing the range of this potentiometer because we have a range from 0 to 1023, and we want to use a MIDI suitable range, which is from 0 to 128. So I want to create other variables, which will be MIDI state. So here, MIDI state at I is going to be the map function, pot state at I. It's first its original range, which is 0 to 1023, and the new range, which will be from 0 to 128. I'm just going to add some text here so it's easier to read. So now we're going to print the words pot state and then the pot state, then MIDI state and then the MIDI state. Then the same thing for the next potentiometers. So you can see here in the left the pot state and then the new range with the MIDI state. Okay, so now enough of simulation, and let's assemble our circuit in the breadboard. Let's add the two potentiometers. Connect the ground pins. Then the 5 volts pins. The common ground to the Arduino ground. The common 5 volts to the Arduino 5 volts. I'm gonna change this ground to this ground just so it looks better, because it doesn't really matter. Then the wiper of the first potentiometer to the A0, and the wiper of the second potentiometer to A1. Now let's upload this code and see if we have the same reading as we had in the simulation. And yes, we basically have the same reading, but pay attention in the pot state, how it's changing the numbers really fast. This is called floating, and this happens because in real life we have tiny changes in the current that's flowing through the Arduino, and even your hand can change this current and affect this floating thing that happens in the Arduino, and this is a natural phenomenon. So now we want to do something very similar to what we did with the buttons. We just want to send values when we are actually moving the potentiometer. And what we want to do now is only send a MIDI value if the value is different from before. This way we will avoid this shotgun of numbers. So let's just do this first. Let's only send this. So if MIDI state is different from MIDI P state. Remember what we did in the buttons lessons? We only send a message if the button state now is different from the state before. So we need to store this pot state somehow. And then in the next reading, we need to compare the state now with the state before. And if they are different, send the message. So here, we're going to store the MIDI state. Okay, so we are getting this crazy reading because we have this serial print line here in the loop. We don't want that. I'm going to delete this and just create this new line here. So we're gonna, if we're moving the potentiometer, we're gonna print pot state and then the MIDI state and then a new line. See that most of the times it stops, but sometimes we still have that thing that's sending notes, that's sending values and values and values. This is because the pot state is changing from our range from 0 to 1023, and this change is actually changing our MIDI state from, like, let's say 23, 24, 23, 24. So only asking to only send notes if MIDI state is different is not enough, because MIDI state will change because of the noise that we have in that pot state reading. So we need to do something else. So one way of doing this is that when we move our potentiometer, the faster we move our potentiometer, the bigger will be the difference between the pot state now from the pot state before. So we need to actually calculate this difference, the pot variation from the pot before from the pot now. So we need to calculate this variation, and if this variation is bigger than a threshold, then a value we will choose means that this change is probably bigger than the noise. So let's say the difference of the noise is like 1, 2, 3, but when we move, this difference is way bigger. It will be like 10, 20. So we need to have a threshold. Let's say we only want to send values if the pot variation is bigger than a threshold. So we need to calculate the pot variation. So the pot variation, we can create the variable here, pot var equals state minus pot p state. So that's why I already have that pot p state here. And we can store the pot p state here. So in the end of our loop, we will store that value, and in the next reading, we'll have the actual state, the state now. So what we want to do is that if pot var is greater than pot threshold, we're going to create this variable, do this. So let's create a variable for pot threshold. Can be a byte because it's a small variable. Pot threshold, let's say 10. So only if the variation is bigger than 10, we are gonna run this thing here. And only if the MIDI state now is different from the MIDI state before, we're gonna do this. Oh, another thing, our pot variation can't be negative, because if the value now is 10 and the value before was 20, 10 minus 20 is minus 10, and we don't want negative values, so we want only positive values, so we can change any negative to positive in this way. We want the absolute value, so ABS, and then inside the parentheses that we want the absolute value. So you see that's not working properly. That's probably because our threshold is too big. Let's decrease this number or 2, so our variation only needs to be 2 numbers, for example. Okay, now you see that only when we move, but sometimes you can see that it's changing by itself, so let's increase this to 3. Yeah, we're getting there, but see something. We have the reading 30, 32, 33, 35, 36, 38, 40. Let's increase a little bit more our threshold. Okay, so the reading is pretty weird, and the reason for that is that I made a mistake here. I want to store the pot P state not here, but here, because otherwise the difference will be always too small, because you're looping very fast. So the reading of the pot state is right after the reading of the pot P state. So our pot var is rarely bigger than the pot threshold. So we actually want to put this here. And it's nice that I do those mistakes here, because those are common things and you need to think a little bit to find where the problem is. So let's see how it goes. Okay, so much better. But let me show you something. Let's increase this pot threshold to 15, let's say. See here our MIDI state, 14, 16, 18, 20, 22, 24, 26, 28. See that we are skipping some values. That's because we are only sending MIDI when we have a big change in our movement, which means that between here and here, between this big change, we are missing the numbers in between. So now we need to apply an algorithm to fix that. So the way I do is like when you move the potentiometer, you open a gate and all the readings come through that gate for X milliseconds. So you move and that gate opens, and if you stop, that gate will be open for more X milliseconds. So every time you keep moving, the gate keeps open. It only closes after you stop, and then it waits for X milliseconds. So it's pretty similar to debounce, but it's the opposite. With the button debounce, when you pressed for the first time, you didn't want to read anything for X amount of milliseconds. Now it's the opposite. When you move for the first time, you want to read everything for X amount of milliseconds. So we need to create some variables. I'm gonna create the variable pot timeout, and this will be how much time the gate will be opened. So we'll choose, let's say 300 milliseconds, and that's an arbitrary number, could be a little bit more, a little bit less, but I found this to be a good number. Sorry, this needs to be a const int. A const int is a variable that won't change during the code, so we're never gonna change this variable, just like this byte. We're gonna need an unsigned long for previous time, so that's previous pot time, and the pot timer. Okay, so we want to store in the previous pot time when we move the potentiometer. So when we moved the potentiometer, it's when the pot variation, the pot var, is bigger than the var threshold. When the variation is bigger than the threshold, means that we moved the pot. So then we can store the time now, that millis, the millis function, in that ppot time. So let's change some things here. Let's take out of here. So now when the pot variation is bigger than the pot threshold, we want to store that time. And here we want to keep track of how much time has passed since we moved the potentiometer. So it's millis minus that previous pot time. So what we can do here is that if pot timer is less than the pot timeout, do this. Okay, so a quick recap. First thing, we read the analog pin. Then we change its range. So we have these two variables we can work on. We calculate the pot variation, subtracting the state now from the state before. So if the variation is bigger than our threshold, we record the time now. To know how much time has passed since we recorded that time, we calculate millis minus that variable. So if this timer here hasn't reached 300 milliseconds, or if it's less than pot timeout, we can do all those things. So let's upload this code and see what happens now. Let me just label this before. See now that we have all the values, we don't skip anything. 32, 33, skipped a little bit here, but it's not a big deal. You see that we'll have some 34, 33, 34, 33, but in the MIDI world, just one value, it's really difficult to hear. But there's a way we can make this even better. A lot of you ask me how I can smooth my analog read, because we have this floating, this noise thing that makes our signal jittery, and there are ways to smooth this reading. And my favorite one, which is pretty easy to use, is using the library Responsive Analog Read. So we need to install the library. You can search Responsive Analog Read here in the Library Manager. You can install it here. Okay, so the way you use this library, first you need to create these variables, which is snap multiplier. The snap multiplier is for making the reading more or less smooth. The value I use is 0.01, and you need to have one instance for every potentiometer. Don't worry about what a class instance is right now. And here in our loop, you paste this because here we are initializing each instance of that class, and here we are setting the resolution of our analog pin, which is 1023. Don't worry, some new things here, but just do like that and you will be able to smooth your reading. And the next thing I'm gonna do, I'm going to create a new variable, which is pot reading. So pot reading at I will be our normal analog read. I'm just changing the variable to another name. Then responsive pot at I dot update, and what we are updating is this value. And then here in pot state, we are not reading the pin. What we are doing is responsive pot at I dot get value. And we don't need to do anything with our MIDI state. So now I want to add some prints so you can see actually the difference between the normal reading with the responsive pot reading. So I'm going to comment this, and I'm going to paste those prints after our loop. So I'm just printing the first potentiometer so it's easier for us to visualize. So first I'm printing the raw value, then I am printing the responsive read value, and then the MIDI state value. Now see the difference. The raw value is always jumping while the responsive read is super sturdy. So for you that always ask me how to smooth your reading, that's how you do it. And if you made it so far and if you are liking it, please press that like button. And the only way I'm able to keep doing these videos here in YouTube is because of my paid courses. You can check here the Nerd Musician Pro, which is my complete course on how to build MIDI controllers. There I teach you how to build them without actually having to code yourself. I teach you how to adapt my code, only changing some numbers, so you can use buttons, potentiometers, rotary encoders, motorized faders, displays, LEDs. I teach you how to do MIDI Bluetooth controllers, plus a community with more than 1,000 students, me, and personal support. So if you're really thinking about building your MIDI controllers, I really advise you to go there and check them out. So now that you know how to smooth your reading, let's come back to what we had before. And let's see how is our reading. Now our reading is super fast and smooth. And then the next thing is sending MIDI. For that, we're going to use our MIDI USB library. I'm going to paste here at the end of my code those functions that we're going to use with the MIDI USB library, either to send note on, note off, or control change. Today we're going to send control change. And the way we send this control change is control change, and then the channel. Let's create a variable which is called pot channel. Then control, which is the CC number we want to send. So we created the variable pot CC, I guess, at I, and then the value. The value will be MIDI state at I. Then we need to type MIDI USB.flush. Always when we want to send any MIDI message with the MIDI USB library, we need to put MIDI USB.flush. So now if we upload our code, oh, I forgot to create the variable pot.ch. And as a reminder, in the MIDI USB library, the first channel is actually the channel 0. Let's upload. Let's open MIDI monitor. We should see Arduino here. So we have Arduino Leonardo, and you're sending MIDI in channel 1, CC11 and CC12. You can change the CC here. So let's open Ableton. Let's go to Preferences, MIDI, and make sure that our Arduino Leonardo is selected in track and remote. I'm going to drag a loop here. I'm going to add an auto filter. I'm going to map the frequency with my first knob and the reverb with the second knob. You can see that I can move here and here. So that's how you code potentiometers to use with your Arduino to make your DIY MIDI controller. One thing you can do here, if you want to add more potentiometers, you just change end pots to whatever number, and here you put the pins that they are connected. So I hope you enjoyed it. I know that coding can be a little bit confusing. You can feel your brain leaking throughout your ears and your nose that death is coming, but it's super fun. For me, it is a creative process. It exercises my brain, and for me is the best thing to combine with making music. The link for the code is here in the description, and if you like making things and making music, I'm sure you will love making your own MIDI controllers. So please check my Nerd Musician Pro in the links here below. The Nerd Musician Pro is made of 3 different courses: the Making Music with Arduino, where I teach you how to build MIDI controllers without actually having to learn how to code, only adapting some numbers to my template; the KiCad PCB Design, which is a course where I teach you how to design and manufacture high-quality printed circuit boards for your MIDI controllers; and the Arduino Programming is where I teach you how to code, which is like we are doing now, but with more content that's not covered here yet. And also it comes with a private community with more than 1,000 students. We have support, a guy that's there just to answer your questions, and also you have my contact so I can help you with your projects. And community and support is probably one of the most important things you can have, and you're gonna need it. And subscribe if you didn't do yet, and please press that like button, and leave here in the comments if you have any questions and any suggestions for future videos. Ciao!